Good afternoon, evening, or morning, wherever on the internet you may be, and welcome to Azure Conf 2014. My name is Rick Garibay, and it's my pleasure to be with you here today to talk about service-assisted device communications on the Microsoft Azure platform. A little bit about myself. I'm a VP and Distinguished Engineer leading the development platform group at Neudesic, a leading Microsoft managed partner, currently focusing on the Internet of Things, intelligent transportation, and hospitality and gaming solutions. And I'm an 8-time Microsoft MVP, most recently in Microsoft Azure. And there's a number of ways that you can catch up with me both during and after the session today to continue the conversation. As a quick reminder, you're welcome to post questions by using the Azure Conf hashtag, and any questions that we can't get to as part of this session, we will be happy to continue the conversation post-session and throughout. So I want to start today by just setting some framing on 4 key areas that I want to spend some time talking about. First of all, I'd like to share kind of the magnitude of the Internet of Things. If you're tuning in, chances are that you've heard a lot of the buzz around IoT, and maybe you're doing IoT yourself. So I'll spend some time just kind of setting some context around what the Internet of Things is all about, and then talk about the proliferation of devices, protocols, and messaging models that you want to think about as you start to plan your Internet of Things solutions. I'll also hope to leave you with one goal, and that is to change your perception of what the IoT is all about from merely things on the internet, and the difference that the Internet of Things at scale and the value that that provides from a business and technology perspective by taking advantage of data-driven insights and action at a distance. And then last, I'm going to share with you the current thinking at Microsoft, particularly on the Azure team, around service-assisted communications on the Reykjavik device gateway. So with that, let's talk about the Internet of Things by the numbers. One of the few things that analysts agree upon across the sphere is that this thing is called the Internet of Things is actually pretty big. So on the low end, you have firms like Ericsson and other leading research firms coming up at 20 to 50 billion internet-connected devices by the year 2020. So get your head around that for just 1 minute. In about 5 years, 20 billion to 50 billion internet-connected devices on the internet. Somewhere in the middle, you have IBM coming in at 75 billion devices. And then on the high end, kind of the bullish CIO magazine and journal coming in at 212 billion devices connected to the internet by the year 2020. Microsoft has been doing some research and thinking around this space, along with many other platforms, and they predict that just in 3 years, 2017, we will have a nearly $2 trillion Internet of Things market within the overall space, ranging across industries. And we'll talk more about the different industry type solutions and what we're seeing in the field and how we think that Azure is a great platform for tackling a lot of these opportunities and the challenges inherent with delivering those opportunities. So let's just level set on some terms. There's a lot of different definitions for what the Internet of Things is all about, but the term that I like is really the idea that you give a physical object the ability to communicate on the internet with one another and other objects in its environment to communicate and interact internal and external states across its environment. And that context really is what all the excitement around IoT is really all about. So let's talk a little about the devices, protocols, and different patterns that exist today and that you're likely to encounter and have to really reason about as you employ your own IoT solutions. Or maybe you're already doing IoT and can stand to improve or modernize your current technology landscape. When you think about devices, you can kind of categorize them into the following 4 categories. On the large end are embedded devices that you've likely been interacting with for quite some time. So when you go to an ATM or you check into a kiosk, those are what we're talking about in terms of large devices. And on the mobile front, devices that are not too different in terms of computing power from those that are sitting in your pocket, that are very ruggedized and built for purpose. So the example there might be when you return your car rental after a business trip, the agent comes, maybe scans the VIN or some RFID identifier on the vehicle, asks you some questions, and then follows a workflow to get your receipt. If the agent drops the handset on the ground, no big deal. That's really what it's built for. And so those areas are important, and if you've done any amount of embedded development, you're going to feel right at home with a lot of the fundamental aspects of what you need to think about when you're doing Internet of Things type development. But really, when you talk about IoT at scale, we're really talking about the bottom features or the bottom examples. controls, and that being the small and micro devices. So by small devices, we're talking about things like gateways, wearables. There's certainly a lot of traction right now around smartwatches, the idea being that smartwatch provides a portal into kind of your world. But without that smartphone, without that gateway in your pocket, there's not a ton of value gleaned by those devices. And so at the micro level, what we're really talking about is microcontrollers, sensors that are capable of interacting with the outside world and each other to really provide a new way of interacting with the physical world. Now, these devices range in terms of size and footprint. So as you might imagine, on the large end are the devices that you're used to interacting with. On the small end are devices that may be new to you, depending on how much work you've been doing in this space. Some of them as small as the tip of a pencil eraser. And the concerns that you need to think about in terms of how you interact with these devices is that some of these devices will be very capable of speaking TCP/IP or UDP or other routable protocols, others not so much so. So the myriad of protocols, both from an application and networking perspective, to really contend with is astounding, and we'll talk more about that here in just a little bit. Some other devices that have been very popular around the maker spaces include that of the Raspberry Pi. So here really you have what's considered probably more of a small device because you're talking at about 512 megs of RAM with 700 megahertz processing power. Now, for all intents and purposes, this is a microcomputer. In fact, there's a lot of examples out there where people have taken this board, built media servers, streaming servers, etc. A newcomer to the space that kind of is in the same form factor more or less is the Intel Galileo. The Microsoft Intelligent Systems team and embedded team is doing a lot of work with Intel around this device. This runs 256 megs of RAM, 32-bit x86 400 megahertz processor. So again, very much kind of in that medium sphere of things, but there's a lot of really cool and fun things that you can do. One of the things that I've learned and I recommend to everybody is if you're getting into the Internet of Things and want to really take it beyond the garage, beyond the maker side of things, and there's nothing wrong with a lot of the wonderful and innovative solutions that folks have put together, is to really constrain yourself to hardware that's going to more or less likely resemble the type of hardware you're going to interact with on the field. Or in the field, excuse me. So one such example is the Arduino Uno. So you could argue that the Arduino is really what started this all for the hobbyist and maker. And to give you some perspective and contrast to the previous two devices that we talked about, the Arduino Uno runs at 2 KB of RAM with 16 megahertz ATmega CPU. So your resources are tremendously constrained compared to the other two devices. What I would say is kind of the Arduino's cousin, a relative newcomer to the space, is the Arduino Plus 2. So pin compatible with the Arduino, meaning that a lot of the sensors and shields that have a very strong and rich ecosystem in the market are compatible with Arduino, but Arduino running a micro version of the .NET framework called the .NET Micro Framework. And the Arduino Plus 2 comes in at 100 KB of RAM and 168 megahertz running a Cortex M4 32-bit processor. So a little more robust than that of the Arduino, but again, much more similar to kind of the environments that you're going to find in the field. One device that I like that's kind of somewhere in between is known as the Gadgeteer Fez Spider. It's actually a device that I'm going to demo here in just a few slides. This device is very modular in nature, so one of the things that you'll find if you're new to the Internet of Things is getting your head around digital electronics. So the first time that you actually succeed at completing a digital circuit will be the result of actually, a lot of learning if you haven't come from an embedded or digital electronics background. And so the devices I shared before do require some knowledge around that, but what I love about the Fez Spider is it's very modular in nature. And I'll show you an example of that here in just a moment. You can basically snap in all of the different module sensors, etc. And we'll actually show that here in just a moment. So really, all of these devices are very interesting and provide you with a great prototyping environment to either have fun or actually test the waters on a new idea or solution. But really, the point here is that beyond the garage, the true significance of IoT is the potential that it creates for providing insights and being able to take action on those insights to enable new business capabilities. And really what we're talking about here is a difference between merely having a thing on the internet and taking advantage of these devices that now have the ability to communicate with each other and the outside world at scale. So I mentioned some of the industries that are really in focus here. And the reality is that I can't think of a single industry or vertical that isn't affected in one way or another around IoT. So whether you're talking about the ability to track parking in a municipality and to understand when a vehicle parks and leaves its parking space and be able to make decisions around pricing and whatnot, to understanding how your consumers are using your coffee maker or other devices. These are the types of things that we're starting to see become very, very mainstream. I'm sure that no doubt everybody here is very aware of the Nest thermostat, massive commercial success, and underneath that very sleek and sexy shell is a microcontroller no different than the ones that I shared with you today and the one that I'm going to spend some time talking with you today. So one of the things that I feel very confident about is there really isn't a single industry that isn't left untouched by the opportunity and the promise of the Internet of Things. Healthcare, the idea of monitoring and remotely managing disease, oil and gas, utilities, being able to stream data from homes and commercial spaces to make more informed and smart decisions about usage patterns and monitoring and managing energy consumption. The possibilities and the opportunities are really, really endless. So what this really signals is a shift from the IT way of thinking about how we map technology capability to a business outcome. In IT, we spend a lot of time thinking about applications, running those applications on servers, managing those composite applications as systems. And that still is very fine and good, because one of the things that makes the Internet of Things so viable is that all the technology and all the capability actually already exists. So if you think about cloud computing and mobility, both of these capabilities from a technical perspective are mainstream. They are accepted and are adopted and are maturing at an enormous pace. So you bring those two together, and that's really unlocking the potential around the Internet of Things. And so really the shift of focus here is from merely thinking about IT or information technology to operational technology. The shift from servers, applications, and systems to devices, telemetry, and understanding how to interact with these devices from a command and control perspective. So the output of that and that intersection really is the opportunity to glean new insights via the data being shared. And before the session, Seth Juarez did a great session on machine learning, which is definitely applicable here. And then being able to take action on that data at a distance to actually have an impact, a direct physical impact on the physical environment. So let's drill into that here just a little bit. From a data-driven insight perspective, the whole idea here is that by monitoring this data at scale, right, we're not talking about a handful of devices. We're talking about hundreds, if not thousands, or hundreds of thousands of devices. There's a lot that you're going to learn about how the environment and the usage of these devices. That can help you to be more efficient. It can also help you to learn more about how your customers, your users, are interacting with your products and devices, and help you to target the consumer in a new and interesting way. Also, obviously, discovering patterns, trends that lead to new business insights, new business processes based on usage or identifying inefficiencies, et cetera. And then the ability to take action at a distance basically means that looking at that data as it's coming in and being able to make real-time decisions on that data to maybe send a unlock command to unlock a door or something to that effect, or open up a remote gate, as well as as that data is at rest, doing a lot of the types of analytics that you saw earlier today around machine learning, big data, HD insights, et cetera. So we're talking about the ability to act remotely and automatically and intelligently, which if you think about technology is kind of still a final frontier, right? There's still human interaction, whether you're interacting with a browser or an agent or some kind of device. Here, we're actually creating intelligence around these physical objects to make decisions based on heuristics and algorithms that we haven't really kind of unlocked yet. Remote control, obviously, is a source of efficiency, and again, enabling new forms of customer interaction and engagement. So that's all kind of very abstract. So let's actually jump into some real-world examples of data-driven insight and action at a distance. One is, imagine your single-serve coffee maker. There's probably a lot of people like me that have actually burned through a couple of them. And I'm not proud of that, but I look at it as a commodity. I spent $100 on the single-serve coffee maker. I'm the only coffee drinker in my family, so it works great. But when I brought the coffee maker home, on top of the box with a label that said, make sure that you follow the maintenance procedures for descaling. When I opened the box on the cellophane, there was another label that reminded me of the same. I couldn't get to the machine without seeing 3 or 4 messages reminding me that about every 3 to 6 months, you want to go ahead and run a descaling operation, particularly if you live in Arizona where the water is very, very hard. So think about this in the context of now this coffee maker actually installs a sensor that's very smart and capable of just doing mineralization reads to figure out the hardness of the water, and basically is streaming that telemetry up to some API, some backing store. Maybe it's keeping tracks of daily work cycles, how often the coffee machine is being used, and then maybe based on an opt-in model, identifying different flavor trends. So I like very robust, bold coffee, and there's probably a lot of vendors that actually support the form factor for the coffee, single-serve coffee machine that I use that would probably love to make me aware of their product. So if you think about those three examples on the insight side, well, the action that you can take is imagine that one day you get an email from the manufacturer asking for your permission to go ahead and start a descaling operation on your behalf. Absolutely, right? It's nothing I want to worry about. Take some time. I have to rinse and repeat and a number of different things. And ultimately, I drink coffee, so I'm always on the go. Don't have time for that. So that would be a great way to maximize my customer experience and really start to deliver business as a service or outcomes as a service. Understanding daily work cycles and maybe making the observation that you've bought the kind of single serve, coffee machine that's designed for maybe 1 or 2 cycles a day, and you're actually using it 5, 6, 7, 8 times, and in a few months you're going to burn out the machine. Let me actually credit you up for our small and home office version of the machine and give you a discount for being a loyal customer. And then obviously on the flavor trend side of things, unlocking new opportunities around alliances, e-coupons, etc. So this is just one example. Taking a very generic, personal coffee machine. But we're talking to a lot of customers today that actually have very similar things, whether you're talking about, manufacturing systems, small home office, large type automation systems, copying, printing type machines. This is really now the difference between the cost of doing business and just differentiating yourself enough to provide these types of things that customers are going to start demanding as more and more vendors and companies start to get on board. Another example I kind of mentioned earlier on is smart parking. So imagine that when you park in a big city downtown, there's a notification that's sent when you've arrived and when you've left that parking spot. Also keeping track of your payment information and sending you an alert when you're maybe 5 minutes away from expiry, so that you can advance that or extend that parking spot from the comfort of the meeting that you might be at downtown. Allow your customer to set dynamic pricing, with the idea being that when parking is very full, the price to park is at a premium, and when it's less congested, not so much so. And then obviously being able to drive revenues for that municipality by providing directed enforcement. So as opposed to employing X number of people to just kind of wander and see if any meters are expired, now you have 1 or 2 individuals, give them a tablet and a heat map, and basically allow for much more efficient use of resources and driving revenue for that municipality. The last example I'll use is product placement. This is one that you are probably already contributing to, whether you're aware of it or not. So you walk into a major retailer, I won't name any names, you may be opting in to use protocols like iBeacon that provides a signature around proximity of you and your app and a actual product, being able to monitor foot traffic, and it's not always just opt-in, right? So your devices emit a anonymous signature, whether you know that or not, unless you turn off all networking. And so that's anonymous usage patterns, but it's very valuable to a store, to a retail store, to understand what are the traffic patterns, right? Where are the clusters of customers spending most of their time to push the most expensive or higher margin products in that category. So these are just some examples of things that we're seeing today and actually working with customers today that's very, very real, and I think it's only going to get bigger. So let's actually shift gears a little bit now, kind of beyond the business type scenarios into kind of the technical aspects of how to make these types of things possible. It turns out that Microsoft has actually been spending quite a bit of time in this space. This is work that's been led in large part by Clemens Vassars, Todd Holmquist Sutherland, and Dan Rasanova's team on the Azure Service Bus team, who, by the way, I'd like to thank, because without their support and kind of bringing me in, this talk would not be possible today. But it turns out that you can group the interaction or canonicalize the interaction between devices and the outside world into two main categories. The first category on the left are messages or interactions that originate from the device. So the device has the ability to talk over some kind of a network protocol and voluntarily sends usage information known as telemetry to some backing store that then does something with that data. When something is abnormal, you can detect that pattern and potentially take preventative action. And that's very, very popular in the manufacturing world, where you have multi-million-dollar machines that when the temperature is high or the RPMs are abnormal, chances are it means something's wrong and you want to get in front of that right away. The other thing the device might do is ask a question of the outside world in order to perform a operation. So take, for example, the automated maintenance for the coffee maker. The coffee maker may make a request to the user profile to make sure that you've enabled the policy to allow that coffee maker to start its descaling process, as one example. And so again, this is typically a request response from the device to some API, some command source in the outside world to ask a question. And then the exact opposite of that is actually commands and notifications. This is now interacting with the device from the outside world looking in. So I want to ask the device to do something on my behalf using a command. One idea may be, yes, go ahead and start a descaling operation, or open the car door that you may have sent a request over your smartphone, as well as a notification to make the device aware of some new fact that it should be aware of in order to continue to process in its own way. As you might imagine, the left side of the slide here, telemetry and inquiries, turns out that's easier, right? We've been actually building applications and have the entire web built on this model of request response, typically stateless, although not all IoT protocols are that, and we'll talk about that here in just a moment. But what gets a little bit more challenging is, we're not talking about having one or two devices or even a dozen devices, but imagine managing thousands of devices or hundreds of thousands of devices and being able to, assuming you can communicate with that device, keeping those devices straight and being able to address and manage and scale those devices as well. And so as you think about those patterns and you kind of overlay those on the application and networking protocols that are out in the field today, the myriad and combinations of these is absolutely astounding. So, I talk to new customers all the time that either employing, something maybe like 2G or Wi-Fi or LTE, but then that ellipsis that you see there is really representative of a lot of these environments have actually, figured this out on their own and have implemented their own custom protocols or application protocols. And so, certainly you can kind of bet on some of these protocols as being pretty prolific, but don't underestimate the custom protocols that exist out there in the wild either. So let's now shift focus from the messaging patterns and protocols into how people are actually doing IoT today, right? Because the reality is that IoT isn't something that's coming, it's already here, and folks have actually been doing IoT for quite some time. So the first model is what we refer to as the default connectivity model, and this is where you basically give every device a IP, assuming that it is capable of talking over a routable protocol. Now, obviously, that's going to be an IPv6 address because you'll run out of IPv4 addresses pretty quickly. So you give it an IP address, and then the device is responsible for exposing some kind of an API for control query operations, and obviously has the ability to then use its client networking stack to make requests, inquiries, etc. The idea here is that the command source might be on-premise or remote on a different subnet. Oftentimes it will, and that remote access is just enabled with VPN in the VPN routing domain. So let's take a look at a picture of what this looks like. You have the device on the right-hand side, the command source on the left, and the device basically exposes a service API, maybe using HTTP or TCP or some kind of a socket-based protocol. Connections are command source initiated, so the command source, some API living on-premise or somewhere else, negotiates a handshake, can identify the device, and then sends messages to the device. Well, let's talk about, and this is how, by the way, many implementations have been delivered today. So let's talk about some of the challenges with this approach. Well, first of all, from an addressability perspective, once you're managing devices at scale, talking about 1,000, 10,000, 100,000 devices, it gets really hard, even with a plethora of IPs that IPv6 provides to actually keep track of these devices, right? And by the way, it doesn't work for devices that are loosely coupled. So I do a lot of work in the intelligent transportation space. Imagine a commercial vehicle, a semi-truck that's basically cycling from Wi-Fi tower or cellular tower to cellular tower. This model just basically breaks, right? You're getting a new IP address as you're moving almost every few miles. From a security perspective, the problem here is that some of these devices, number one, don't even have the resources to do SSL or TLS, right? They can't even validate a certificate chain. So one of the problems that you have here with some of the smaller devices like the Arduino and Arduino is SSL, TLS isn't even an option. But beyond that, the problem here is that you're taking this little, poor device and not only asking it to host its own network stack, but defend itself on top of that. And this is where you start to see denial of service attacks, and there's been a few in the news that I won't repeat here, that actually is a big problem. And the amount of laxness and security around some of the solutions that you see in the market today are pretty significant. And then, of course, as I mentioned earlier, from a scalability perspective, VPN just isn't the answer from a security perspective or a scale perspective. And you're not going to be able to address, 1,000, 10,000, 100,000 devices in this model, right? It just simply breaks down. For smaller implementations where maybe you've got, a couple hundred of devices, maybe this will work. We actually did this for one of our clients where we're basically automating the raising and closing of a gate based on an RFID read. Have probably a dozen different locations. This is probably going to be fine from a maintenance perspective. But beyond that, it really becomes a security nightmare. Not to mention that, aside from VPN, you're having to open up ports, and we all know how that conversation goes, right? When you go to your IT security admin and say, hey, man, you mind opening up an inbound port for this IoT thing? And they go, yeah, no, right? So default connectivity, has its merit, but definitely you run up against some challenges pretty quickly. An improvement on that is to basically leverage some kind of a pub-sub broker model where you have a device that now still has its own routable IP address, likely an IPv6. You can secure the device in bridge networks over VPN, and the key really is on bridge because VPN is not really a security feature. And the idea here is that the device participates in a pub-sub message exchange with some on-premise broker that might be doing some industry standard protocol like MQTT. Let's actually take a look at what that looks like. In a logical sense here, this is a huge improvement over the default model, right? Because the device and the command source don't need to know about each other, right? The device basically makes a single outbound connection as a subscriber to the broker. The command source, and that's typically going to be a socket connection, right? Typically, you want to maintain that session or that connectivity. The command source then communicates to the device through the broker, right? So you don't have to keep track of all the IP addresses now. The broker now is responsible for registering that client and then basically marshaling the messages back and forth, whether that's telemetry or commands, notifications, et cetera. And of course, that command source must be either on-premise or bridged via VPN or some other mechanism. So this is definitely an improvement around addressability, right? Because I don't have to keep track of all these devices. Pub-sub helps me loosely couple the relationship between the device and the command source. Doesn't really address the security issues. And from a scalability perspective, again, VPN infrastructure can be costly to maintain. Chances are a lot of that data that's being generated by these devices, landing in some kind of a backing store, having the luxury of big iron behind that, not having to worry about VPN, a lot of the constraints around scalability that introduces, as well as really thinking about how to scale and how to meet the needs of these devices, both from an ingress perspective and an egress perspective, is actually something that there's been a lot of thinking at Microsoft about. And that's really where an improvement over the previous two models comes in, which we call service-assisted communications. The idea around service-assisted communications is to build on top of this idea of having a broker, right? So that's a great start in terms of of addressing the decoupling problem, minimizing the attack surface of that poor device that actually is barely maybe capable of even exchanging messaging. And the idea here is to embrace open standard protocols, right? And so, The reality is that these devices, the heterogeneity of these devices, the application and networking protocols is just so diverse that embracing those as a whole and creating an extensible way to actually interact with these devices is really, really key. So whether you're talking about HTTP or AMQP, which turns out is native on Service Bus and AMQP 1.0, to be very clear on that, or MQTT and CoAP, two protocols that are certainly very popular in the IoT space. The services communication model really embraces this variety. And then the idea here, very similar to the brokered model, is to basically take that broker, that pub-sub relationship, and create an inbox and an outbox for the device. So the idea here is that the device sends telemetry and routes the service invocations via its outbox, right? So think about the device basically sending voluntary information into an outbox that then gets picked up by some other process, given kind of the canonical broker model. And then it's always listening for devices within its inbox. So is there a request to perform some operation? And that's the same way that notifications and inquiries would also be managed. You can correlate requests and responses, right? Because sometimes you might be asking a question of the device. By making an inquiry, that device is going to pick up the question on its inbox, perform some logic, and then provide the response from the outbox. And the idea here is the device knows and only has access to its own two URIs, right? Its inbox URI and its outbox URI. It doesn't talk to any other devices or any other APIs, and there's only one way to communicate with that device, and that's through its own private, secured outbox. So let's actually take a look at what that looks like a little bit closer. Here I have my device. The device basically initiates a connection outbound using the standard default NAT firewall topology that's basically prolific throughout all networking environments. From there, the device doesn't listen for unsolicited traffic, right? It's only talking to its outbox or listening for commands, instructions on its inbox. And then that request basically makes its way naturally using all outbound ports, right? So no port magic, no asking your security administrator to please open up an inbound port. The port mapping is automatic. And outbound, your attack surface is severely constrained, right? Because there's only the ability for the command sources to talk to that device's inbox or that device's outbox, provided there's a security handshake that takes place, maybe using shared key type authentication. And now you can have as much big iron behind that to handle all the processing, your command sources, providing machine learning, big data solutions, all of those things that then can communicate and interact with your devices at scale. So let's actually take a closer look at what that might look like. If you think about this inbox-outbox metaphor, it turns out that Azure Service Bus is perfect for this type of design. Looking at telemetry routing with Azure Service Bus, the idea here is starting from left to right. Your devices are basically sending voluntary information to a topic, and that's basically just a URI, and you could use HTTP or any combination of client-side APIs, but HTTP tends to work very, very well. You may use AMQP depending on the resources available to the device. The device, obviously, in the service bus model must be capable of doing SSL TLS, but the idea here is that the devices can send messages over the Azure Service Bus in the inbox, or the outbox, excuse me, and then you can set up filters, right? Because you want to be able to split the stream between just regular normal telemetry, right? Machine data that's interesting maybe at rest, or maybe you want to do some real-time analytics on it. But when something's wrong and there's an error, a fault, or an alert, right, you want to basically fast forward or first class that message to the receiver. And so you can use filters that are native to Azure Service Bus. I won't have a lot of time to go into too much more detail there. And then subscriptions, right, that basically are determined by the filter condition. And so you can have an alert processor that is high priority, right, that's monitoring that subscription, or a storage preprocessor that maybe has a partitioned or a fanned out approach for managing a lot of the telemetry data at scale. And out of the box, you get all these capabilities, including parallel processing, the ability to split the stream, using filters and subscriptions, as I mentioned, implementing different quality of service levels. So in the quick example that I shared previously around the idea of being able to remotely send a door unlock command maybe from your smartphone or some other API, that message needs to be received by the device that's managing that lock on your door, and that lock needs to be able to take action on that device pretty much immediately or never, right? So quality of service is actually a very important part of these types of things, and not really simple to implement on your own, right? So these are things that Service Bus provides right out of the box. And of course, being able to level and balance the load, a canonical feature of any brokered system. On the command side of things, right, the whole idea here is that you have devices, assuming that they're all routable and can communicate with Service Bus directly, that are basically receiving devices, right, from their inbox based on commands that are being sent from senders. And the idea here is that you give the device a specific subscription, or maybe you're using queues, and that device basically looks for messages within that actual queue, and that's where things like time to live come in. You can address all the firewall magic by just leveraging that default NAT model. You can deal with spotty connectivity because the commands will just queue up until a network connection is available, and then the device can reach in to its inbox and actually get the work done. So these are some examples of how you might think about an inbox or outbox with Service Bus. One of the new entity types for Service Bus is Event Hub, currently in preview, released not too long ago. The idea here is hyperscale. So thinking about telemetry at scale, fully managed, interoperable, secure, and cost-effective for getting these bursts of data that we're starting to see from these devices over to a backing store to basically do some processing or what have you. And I'll talk a little bit more about Event Hub before we are done here with the session. So enough slides for now. Let's actually show what device direct commands over Azure Service Bus queues look like, which will basically take the idea that I shared earlier and actually put it into action. So I have a solution here that basically includes a couple of types. First is this program. I'm actually using the Gadgeteer SDK, and one of the things I love about this SDK is it provides me with a project template for Visual Studio. So I'll just show that to you here very quickly. I mentioned the modular nature of Gadgeteer, and you can see here that in this particular configuration, I have a multicolor LED, which I'll talk about here in just a moment. And then I'm basically just connecting to the internet over Ethernet. Oh. Looks like I am not projecting, so let me actually fix that problem. Alrighty. Sorry about that, folks. So this is the reason that I like the Gadgeteer so much, is that it gives me the ability to basically just snap in a variety of different modules. So if I go to my toolbox here, you can see that there's just a plethora of options: cameras, displays, LED strips, Zigbee connectors, you name it. There's a lot of really cool stuff here. But in this implementation, I'm simply just snapping together a multicolor LED along with the Ethernet, and that's really all there is to it, along with the actual power source. So let's actually take a look at the actual program. You'll see here that I'm using a number of device-specific namespaces and types here. And if I go into references here, you can see a list of that, as well as the .NET Micro Framework. So these are the assemblies that ship with the .NET Micro Framework 4 and above. And the way I like to talk about working with .NET Micro Framework is if you do any amount of mobile development and you like using PCLs, it's kind of a constrained environment, very, very similar, right? So there's a lot of BCL types and FCL types that are available to you, but you do need to kind of learn to work in a more constrained environment. But the idea here is that there's really nothing too fancy going on here. I basically got a program that's going to execute here, and every device has a different object model and eventing model. But here all I'm basically going to do is, actually, let me go ahead and F5 this so we can show this as we proceed here. While that's firing up, what we're basically going to do is use DHCP. So I have my device here connected to a Ethernet connection, and I can show that to you here. So you can't see the Ethernet device, but maybe, yeah, here it goes. So you can see it right there. I've got the internets there, and so basically I'm going to ask for a DHCP address, as you can see here. So I'll hit F5. And you can see there's a sleep there, and that's just because sometimes it takes a while to get that IP. But here in just about 5 more seconds, we should see that we do have an IP address. And notice that this is a private IP address. So I'm actually going to communicate with this device over a private IP address without any firewall goo or magic or anything like that. And the next thing I have to do is basically ask for the current network time, because the device has no means to keep network time. Every time it runs, it's kind of like a blank slate, if you will. So I'll go ahead and make that call here on line 54. It'll just take a couple seconds, and while we're waiting on that to complete, you'll see here that I'm basically going to be, whoops, let's go ahead and run that one more time. Sometimes the NTP servers can be a little bit finicky. While that's starting to fire back up, you can see here that I've got a timer, and every second what I'm basically going to do is check to see if I have any messages in the actual queue. So let's go ahead and run this again, wait for the IP address. And here all I'm doing is implementing a very, very bare bones HTTP client. It's going to call a read and delete. Let me go ahead and get rid of that. From queue, which I'll show you here in just a little bit. And you can see here I'm just using the REST API for Azure Service Bus queues. Great, so it looks like I've got an IP address. And the demo gods are with me once again. And it looks like we've got network time, which is great. And so now let's go ahead and jump into our timer routine. And what we should see here is the first tick happen about every second. So I'll just let it break here, and I'll walk you through what that rest of the code looks like. So I'm going to go ahead and go into the HTTP client. I'm going to call read and delete from queue, which brings me into the second type here. And in this type, all I'm basically doing is setting up a really bare bones HTTP web request, and you'll see it's pretty verbose here, but there is no fancy framework code, nothing more going on here than simply making a HTTP request and then getting that payload, passing that payload back once we encode it to an actual command router. And so let's actually run that. And what you can see here is that what we're basically looking for is the value of the command type. And so based on that value, it's either going to be red, blue, green, or white. And those are the only modes that I support. Now you might be thinking like, wow, so you're going to change a LED from different colors, big deal. Well, the big deal actually is that I'm doing that over HTTP, over Service Bus without having to do any firewall magic. It just works, right? So that's really the main value here. And obviously, if I can do this, there's nothing I can't do once I understand the APIs and how to manipulate that physical environment. So let me go ahead and run this and make sure that I've gotten rid of all of my breakpoints. And now what I'm going to do is bring up my little camera here again, and you can see that my LED isn't doing anything interesting right now. So I'm going to go ahead and bring up Fiddler. And you can see here that I've got a post and the URI to the Azure Service Bus queue using the RESTful API. And I'm basically just going to change the color to green. Let me just go ahead and remove all this noise first and hit execute. So I get a 201, which is fantastic, right? So the message has landed in the queue, and then the device has basically received that message by checking the queue every second and turning the device green. Let's change it now to blue. Great. And my favorite is we do not actually support fuchsia, and we'll actually get the blinking error condition there. So that is Service Bus direct communications using kind of the fundamental building blocks on top of which we're going to talk more about the current work happening in the Azure Service Bus team, specifically around some of the new capabilities that you'll be hearing about here very, very shortly. So building on those fundamentals, the idea here is that this kind of gets us a long way past the direct default approach as well as the on-premise approach. And this is really what we refer to as service-assisted custom communications over a cloud gateway, right? And so the idea here is that we have circumvented a lot of the issues that we saw before, but what about device provisioning? What about things like connectivity and really managing things at scale? So I created this queue. It's very straightforward, very simple, not a lot of steps to it. But what is the reasoning I need to consider when I'm talking about supporting 500 devices or 1,000 1,000 devices, and now starting getting into sessions or partitioning my service bus topics, et cetera. And then obviously being smart about how I'm splitting the stream, how I'm managing things like quality of service, time to live, et cetera, et cetera. So if you think about this from a very abstract perspective, the reality, as I mentioned before, is that not all devices are capable of routing over the internet. Those that aren't, you need this idea of a field gateway here that you see under column B. And the idea here is that maybe I'm talking NFC or Zigbee or some non-routable protocol, and my job as a field gateway is to talk that protocol natively, terminate protocol, and then on-ramp that message on behalf of that device to the gateway. And then for IP-capable devices, it works just as I showed here today. I have a URI that I'm going to be consuming, either as my ingress or my egress URI, and away we go. And then moving to the right, we have the cloud gateway, which we're showing here as service bus, custom code that's going to do stuff and interact with those messages, commands, et cetera. And then you can take advantage of the platform services on that cloud vendor, and then a third-party selection of services, as well as enterprise systems that you may be interacting with today. So when we're talking about custom code on the Azure platform, this is not an exhaustive list, but we're talking about things like websites, VM roles, mobile services, cloud services, and your own external code. And then obviously you can apply all these capabilities and compose them into interesting solutions, whether you're using Azure Database or BizTalk Services, HD Insights, et cetera. So the custom gateway, and kind of where we're leading here to, is that we believe the Azure Service Bus is actually an excellent capability for addressing the 4 different patterns that we talked about, and addressing the reality that some devices are going to be able to talk natively to Service Bus and others aren't. And so what you'll see here on the left is the pattern I demonstrated with the Gadgeteer Fez Spider, where we're sending commands to the device over an Azure Service Bus entity. And then on the right, you'd have some intermediary that basically is capable of translating and on-ramping those devices, whether that's protocol bridging at the network level or at the application level. And so at Build this April, the Azure Service Bus team, Todd Holmquist, Sutherland, unveiled this new reference architecture known as Reykjavik, also known as the Azure Cloud Gateway Accelerator. And so I've had the privilege of actually working with the team around these capabilities for quite some time, a few months, to say the least. And I want to just kind of jump into what Reykjavik is and how you can actually take advantage of Reykjavik in your own solution. So first, what is the Device Gateway Accelerator codenamed Reykjavik? Well, it's just that. It's a reference architecture that represents the current shape of thinking that the Azure team is currently thinking about as it applies to providing that gateway for the Internet of Things. So 4 key components that I'll touch on here very briefly. First is the custom protocol gateway, right? The acknowledgement that not all devices are going to be capable of communicating over AMQP 1.0 or HTTP, embracing the reality that there are other networking protocols out there, or application protocols out there, for IoT, including MQTT, CoAP, which provides a very nice UDP REST type metaphor, and then again that ellipsis, which basically invites the community to come in and build their own gateways using a very extensible framework, which I'm going to show you here in just a moment. And then thinking about now the ability to communicate with the devices, taking that data that's being streamed from the devices from a telemetry perspective and wiring up a number of adapters. So out of the box, I'll show you today the table storage adapter, but there's also work being done around HD Insight, BizTalk Services, and then that purple arrow represents your adapter, right? So if you're streaming telemetry into Azure because you want to light it up with HD Insight or machine learning, but then you also have a need to bring that down on premise, not a problem. You can write an adapter and bring it down to whatever platform that you're interested in. Number 3 here is the Command API host. This is basically part of the Reykjavik reference architecture, which basically is designed to be able to interact with these devices in a very fluent, very simple, RESTful way. And then last but not least is basically the provisioning service and metadata store. So when you think about, you get 1,000 devices or 10,000 devices at your doorstep, how do you go about provisioning and registering and setting up the security and the handshakes and all of those things? And that's really where the metadata store comes in. Now, I would be remiss if I didn't mention a new service that is currently in a limited preview called the Intelligent System Service, which really represents the melding of the Windows Embedded side of things and the Azure messaging side of things. And ISS actually sits on top of the Reykjavik reference accelerator, reference architecture, as the way to actually manage all the messaging. But as you can see here, you get a ton of additional things like the ability to light up the reporting, out-of-the-box capabilities for doing command and control, integrating with things like O365 and some of your enterprise systems. And so you'll certainly want to catch up on the Intelligent Systems Service, which again, built on top of Reykjavik. But I want to spend the rest of the time here on Reykjavik because this is a technology that's very kind of bare metal and one that I'm very excited about, but you'll certainly be hearing more about ISS from Microsoft. So as I mentioned before, Reykjavik is both a reference architecture and it's actually an instantiation of that reference architecture, right? It's not just pretty pictures and drawings that the Azure team comes out and talks about. They've actually taken it a step further and actually implemented an example of what that looks like, which I'm going to demo here to you in just a moment. The way that this looks once it's deployed up on your Azure subscription is you have a master role and at least one partition role. The master role is an orchestrator. So the master role is responsible for setting up the additional partitions that you may set up, and you can actually have up to 1,000 partitions, or actually 1024 to be exact. Each partition is capable of hosting and managing thousands of devices. What does hosting and managing 1,000 or thousands of devices look like? Well, as you can see here, kind of zooming in from the previous slide before I talked about ISS. At the top here, you basically have your standard service bus protocols and then custom protocols that are implemented via the device gateways, and those basically support the ability to bring messages in to the service bus topics and basically have subscribers that are picking up those messages from a telemetry perspective here via a number of telemetry adapters, and that might be the table storage adapter, the HD Insight adapter, or the adapter that you'll build. And then on the opposite side of things, we basically have the ability to send commands. So here's the command API host there in the bottom right-hand corner, and the idea being that it's basically going to send commands to that specific device's outbox for consumption. So let's actually jump into what Reykjavik actually looks like by actually showing you a sneak peek of the actual bits. I'll show you the actual solution that I've pulled down from the currently private Visual Studio Online repository, but very soon will be made available as an open source offering. And so let's actually do that now. Make sure that I am sharing my desktop this time. Great. So here I have the actual solution. This will resemble what you'll see here in the not too distant future. You can see here that I have a number of projects that represent what I've talked about. So I have an Azure host, a master runtime, a command router, common libraries, et cetera, for doing things like encoding and whatnot. My protocol gateway, my protocol adapters. Here you can see that we are investing, or the team is investing in MQTT. I mentioned two of the telemetry adapters that are in the box today, both for table storage and HD Insight. And I'll be showing you table storage here in just a moment. And then, obviously, telemetry adapter framework, which basically serves as a pump for taking data as it's making its way up to Azure and then moving it into the table storage, backing store, or HD Insights, whatever the case may be. So obviously, we could spend a ton of time going into more detail, but unfortunately, I don't have the time to do that. But what I do want to show you is the tooling. So the current shape of things today is that you have a deployment tool here called DVG Deployment Tool, Device Gateway Deployment Tool, and I'm actually in that tool here right now. And this is the command line interface for actually deploying the master and the partition. So again, the master being the orchestrator and the partitions being one of several that are actually responsible for hosting your partitions, setting up your storage accounts, your service bus accounts, being very, very smart about how to partition your queues and topics. So let's actually take a look at some of these parameters here. You can see here that I've got the different roles that'll be supported that I would pass in, so master or the partition role. I've got, obviously some subscription type things that I need to pass in here and whatnot. The identity provider, you can see here a number of options, including ACS, Azure Active Directory, SAS. The environment name, the tenant name, these are all provided by you, and I'll show you this here in just a moment. Here's where it kind of gets interesting. So after you've deployed the master role, you get busy starting on the partition roles. How many devices does this partition need to accommodate? And this is really where the Reykjavik reference architecture is very fascinating, because based on the number that you provide, it's going to get to work on your behalf and set up the right level of sharding, partitioning, naming of the number of queues, topics, subscriptions, etc. Very, very cool stuff. So once you've told it how many devices you want it to support, how many messages do you expect for that partition or that device to actually receive, be received by the device per hour? So the egress messages per hour. What is the average size of those messages? And then the same thing on the ingress side of things, right? So if you look at the CPI MPH parameter, messages per hour expected to be received from each device. So this is how the telemetry and notifications are happening. And then obviously you have to point it to the actual cloud package and configuration and some other options that you can provide as well. So while now that I've kind of reviewed that, let's actually deploy this. And to do that, I'm actually going to show you what a geo deployment of the Reykjavik device gateway accelerator looks like. There's some configuration here that's basically just setting up some variables in terms of where the actual tool lives. This is just a .cmd file, so it's just a batch file. And you can see here I've got some additional settings on where my master package and master configuration lives, along with my partition package and partition configuration, all part of that source tree that I showed you here earlier. I've got some variables that I'm setting up, and this is just for scripting purposes. So I'm setting up my tenant called NEU, my environment of stage 01, East US, and then my identity provider of ACS, but not the only identity provider supported. I'm going to do my build parameters here and actually build this from the ground up. And then what you can see here is I'm going to go ahead and deploy my master role. And I'm actually going to deploy one partition for each of these 4 data centers. So 2 in the US on the east and the west, and then Northern Europe and Western Europe. So we'll have 4 partitions deployed. Each of those partitions will be capable of supporting up to 2,000 devices. So I'm actually going to go ahead and authenticate to my Azure account. Excellent. And so now I'm going to, whoops, let's do that one more time. All right. Wait for that to return. Not quite sure what's going on here. You're already signed in, okay. Great, all right. So now let's go ahead and actually run this batch file. And what you'll see here is that we're gonna get to work on compilation. Now this will take a good 10 minutes, right? So we'll actually come back to it. We'll check in with it as it's proceeding. But we're gonna do the compilation, deploy the master role, which will include the service bus and storage accounts, as well as each of the 4 partitions across our 4 data centers. So while that's happening, let's jump into the presentation and wrap up with a couple slides and a final demo, and then we'll check in to see how we're progressing here. So 19 data centers, as Scott Guthrie mentioned this morning, so you get the sense of the scale here, right? I can set up to 1,000 partitions across 19 data centers. Definitely a new definition on geoscale. If you think about IoT and the volume and the sheer scale of these devices, this is actually very important to be able to provide that level of business continuity that businesses are actually going to start to bet on. So let's actually bring it back now while the deployment's happening, is hard at work here, and talk about this idea of a space heater. So a space heater basically is responsible for keeping the room nice and cozy, maybe in the winter months. And let's actually take this idea of insight and action. So insight might be streaming the current temperature, the current fan speed, current RPM, and then basically based on those insights, increase or reduce the fan speed based on how hot or cool it is, change the temperature to make it more comfortable, or maybe change the readings interval so that maybe I'm getting data not quickly enough, or maybe too finely grained, right? And actually set up those windows. And so now I want to show you what a first-class device on the Reykjavik gateway accelerator looks like by actually showing you how to do telemetry commands and inquiries on Reykjavik by jumping into a separate environment I've set up here that basically includes this very simple device emulator as a tenant, and walk through that here very, very briefly. So here I have the same solution here. I've got the space heater sample, and this again is basically designed to be very simple. So what you can see here is I've got about 300 lines of code, and just from the top down you can see that I'm initializing some parameters. What is my telemetry interval, meaning how often do I want to send telemetry? What's the default for the fan turning on, this fan speed setting? Is the heater on? What's the temperature setting, in this case in Celsius? What was the last observed RPM, et cetera, et cetera. And then the two key things happening here is one, I want to be able to send telemetry. So let me actually just get to that here. Let me actually go to the send telemetry method. So this send telemetry method is going to execute based on that interval, right now 15 seconds. And all it's going to happen is it's going to go ahead and actually send a reading based on the current values, right? And it's going to automatically initialize, do a handshake with the Reykjavik deployment that I have up on my Azure account, learn its URIs for ingress and egress, and actually start interacting with the gateway from there. So let me actually go ahead and run this. I'll hit F5. Well, that's getting up and running. I want to just show you what another deployment looks like, some of the key artifacts. So first of all, I've got right here my cloud services. And we should actually start to see the master partition spin up that we deployed here just a moment ago. Looks like I need to re-authenticate here. Give that just a moment. Well, that's waiting. Let me just actually pop into our trusty web portal, and I'll show you what I was after there. So here you can see I've got 4 cloud services. This master STG01 is actually the one that just deployed with a tool. And you can see here I've got a previous master that I set up prior, along with a single partition for the space heater emulator demo. I've also got a number of storage accounts here that have been set up for hosting the device configuration, doing the telemetry and whatnot. And then on the service bus side of things, I've got 2 accounts. One is for the master role, and I'll actually show you what that looks like here. So you can see here that I've got a number of queues that have been set up. And if you look at this, it kind of looks like a workflow. And this is actually how the partitions get created, along with device provisioning and whatnot. And then if I look at the actual partition on the other deployment that I actually already had in the oven, you can see that here we have no queues, but we have a number of topics. And in this example, I actually set it up to support 600 devices. And so you can see here that I've got a number of inboxes and just a few outboxes, because it's basically automatically configured and partitioned the service bus topics and subscriptions based on the load that it expects to be able to manage from a partition perspective. And actually, if I go back in here and refresh, we'll probably see that the entities are being created as we speak. So let's pop back into my VM here. And yeah, I don't know what's going on with authentication right now. So let's see. All right, let's fire back up. And we are running short on time, but I'll be wrapping up here in just a couple of moments. So I'm going to go ahead and open up the device gateway solution once again. I won't tempt fate again to try to authenticate here. But let's actually fire this up. And what I want to show you is I'll do a breakpoint here on send telemetry and kind of show you what that payload looks like. And then once we have telemetry flowing to our Azure Service Bus table storage account as part of our Reykjavik deployment, I'll actually show command and control, and then we'll wrap up from there. So looks like I'm up and running. So if I set a breakpoint here, let me just improve this view here for you. This should break here. Right now, remember, it's set to every 15 seconds. Great. So I've got a number of parameters here that I'm using. You can notice here properties. So just to keep the message nice and lean, because we are using AMQP here, I've got my from, gateway ID, I've got total seconds, based on the telemetry interval, my fan speed setting, is the fan on, what's the current temperature, et cetera, et cetera. So I'll F5 here and just let this thing party a little bit. And let me just actually show you here. I've got an empty telemetry table, at least when I started here, but we've probably been running a few cycles here. So I should start to see telemetry flowing in. And let's actually execute that again. We should see a couple records here before too long. And you can see here that I've got some partition key information, row key, all that good stuff. But here's where it gets interesting. This is the from device ID name, the message ID, sequence number, session ID, the time, and then here's all that telemetry that I mentioned before. So if I query that again, now you can see that we've got more messages. So we're getting telemetry about every 15 seconds, but actually I'm a data hog, and so I want to see what's actually happening in a much more concrete window. So to do that, what I want to do is leverage the command API. And the command API here is one that has been created specifically for this actual demo. And you can see here that I've got a very simple MVC Web API API here. How many times can I say API? Everybody drink, no. So here you can see that we've got a very simple controller and a number of supported routes. So I've got the ability to get configuration, update configuration, get all the devices, get the device itself, and different settings. So what I'd actually like to do is go ahead and set a breakpoint here on the get configuration and here. And I'll pop into Fiddler, clear all this goo. I'm just going to call get on this actual device of 2001, which is the device that I've registered on behalf of that emulator on the subscription deployment that I have. So let's go ahead and execute this. And you can see here that we're breaking in. I'm going to F5 in the interest of time, but basically what's happening is that request is going to the actual emulator device as an inquiry. The device is responding to that inquiry by replying with a correlation ID, and then basically making its way back over the API. Now this API is hosted on my laptop, but it obviously would be hosted up as a website, would be a fantastic place for it, or Azure API management. But you can see here that the payload returned is this nice compact JSON that includes a telemetry interval of 15 seconds and then the current fan speed RPM factor. So now what I want to do is I want to change that configuration by sending it a command. And to do that, I'm going to just change this to a put. And I'm going to paste the same payload that I got back and change that telemetry interval to 1 second. I'm going to execute. And you can see here that I'm hitting my breakpoint, which is fantastic. And that should come back here. And you can see now that it's echoed back to me the actual telemetry interval. But just so you see there's no smoke and mirrors, let's go back to the get API. And it's awesome because my device is still blinking, and I keep seeing a blinking out of the right side of the room here. What we can see here is that, in fact, the telemetry interval is 1. So I've probably been talking for at least 5-10 seconds. So if we come back in here to the Table Explorer and I do a query, right, you can see I've got a ton more records. And if I just sit here and refresh, so we got 41 records. The telemetry adapter does batch, but we should see this count increase here momentarily. So you can see now we grew from 41 to 55, and the different readings, obviously there's some randomization happening, but you might take an HD Insight view or a Power View, like Yarn or whatever, or Power BI, Power View, and light this up in more interesting ways in this little Table Explorer. But what you can see here is what a first-class device looks like on the Reykjavik Gateway Accelerator. I've shown you telemetry as well as commands and inquiries. So I know I'm bleeding over time, and I'm getting the wink here. So let's just go ahead and wrap things up. Event velocity. One of the things I want to just share, and I'll just kind of bypass these slides, is that new capability in Azure Service Bus Event Hubs is a first-class entity for really doing high-burst telemetry. So the really nice thing is that Reykjavik, what I demonstrated today, was just the vanilla ingress URI that supports Azure Service Bus topics, but Event Hub is supported as well, and so you'll have the ability to toggle that, as you can see here, Service Bus messaging, including Event Hubs. With that, I want to thank you very much for attending Azure Conf. I've had a blast. I'm happy to continue the conversation after the fact. Feel free to hit me up on Twitter or drop me an email, and have a great rest of the show.